Beautiful. All right, so there's a couple of things on that assignment that just gave back, that assignment 4-1. One was the one with the, you have 0.5 kilogram mass to be attached to the balloon to it, okay? And you had to draw the free body diagram showing all the forces. And so here's the deal, whether the balloon is attached or not, and this is going to be relative to what's going to happen today with this whole idea of net forces. Whether the balloon is attached or not, is that going to change that attraction between this object and the Earth?
No.
No, that's still a fixed value. Whether the balloon's attached, I'm pushing it down, throwing it up in the air, it doesn't make any difference. Nothing is going to change the gravitational attraction between that 0.5 kilogram mass and the Earth. So that gravitational pull is going to be negative 4.9 newtons. Boom. That's it. Spot on. Now, if the balloon is not attached, then, and it's just sitting on the scale, then the normal force, which is what the scale is measuring, is going to be 4.9 newtons, because it's all balanced out. 4.9 plus negative 4.9, I get 0. I don't have an acceleration. Okay? Now, you attach the balloon. So, and as long as that thing isn't accelerating, all the forces have to add up to 0. So once you attach the balloon, now there's 3 forces that are in play. I still have the same gravitational pull, but now the normal force, which is what the scale is going to read, is going to read 4.8 newtons because the balloon is applying an upward force of 0.1 newtons. So everything still has to add up equal to 0. And what a lot of you did is you said, well, the normal force is still 4.9. It's not, because if I take 0.1 plus 4.9, that gets me 5. I have negative 4.9. That ends up with an overall net force of 0.1 acting upward. If that's the case, that mass should have been accelerating upward and not sitting there on the scale. Okay? So whenever you see something at a constant velocity, make the forces add up to 0, no matter how many there are. Now, you had the one where you were pushing it along at a constant velocity of like 5 meters per second for 6 seconds, and then you stopped pushing and you had this action. So here's the deal on this velocity time graph. If your velocity time graph is horizontal, does that mean there aren't any forces acting on the system? True or false? A horizontal line on a velocity time graph indicates that there are no forces acting on the system.
No, they just cancel out.
Okay, well that's one option. Okay? One option is that the forces just cancel out. The force that it takes for you to push it is balancing out the frictional force that's overcoming. Gravity is acting down, the normal force is acting up. But no matter what, when you have a horizontal line, that just means that your net force is 0. And when you have a 0 net force, what's the value of your acceleration? 0. Which is why this line is horizontal. Now, you stop pushing it, right away you start to slow down. So if you just look at your graph, go, oh, I've got to have a negative acceleration. Well, the only force left in town is that frictional force. So you had to come in here and say, hey, I got a negative force of negative 17.9 newtons. Divide that by the mass, you get that acceleration of like negative 3.73. So here's the deal. Listen to me, listen to me, listen to me. If you have a constant horizontal slope on a velocity time graph, that can happen one of 2 ways. Either you have a bunch of forces and they add up equal to 0, or you're in a situation like you're in deep, deep, deep space, where if I give something a push, it's just going to move off in a straight line at a constant speed. So you have to have a horizontal line on a velocity time graph. You have one of 2 situations. Either there are absolutely no forces acting on it, and the inertia is just going to keep it moving, but that's only if you're in deep, deep space, or the forces balance each other out. Because even like when we were out there in the hallway and we gave the hockey puck a kick and it was like, you know, it was like on hover mode, there were still forces acting on it. You had force weight and force normal. There weren't any horizontal forces acting on it because we didn't need to, because it was a frictionless surface. So if you're going to change the slope of a velocity time graph, the only way you can do that is to change the acceleration. The only way you can change the acceleration is to change the net force. Okay? So it boils down to a logic problem. So whenever you see something changing on a velocity time graph, that means you're changing the acceleration. That means you're changing the net force. Okay? That's the only way that it can happen. Okay? Cool with that. Okay, now let's talk about that net forces assignment from yesterday. So if you look on kind of 1 and 2, I'm going to give you some hints on number 2. Well, number 1, your first answer on number 1 should be a really big number, like something times 10 to the 5th newtons. Okay, should be a pretty big number. You're stopping at a pretty big truck. So, and this is just a little thing you can do mathematically. So on number 2, you want to find mu, which is force friction over force normal, right? So there's a couple of different ways that you can calculate force friction. This is what we talked about. One option is that I pull it along at a constant velocity. However much force it takes, that's how much it takes to overcome friction. That doesn't work with the semi, okay? Because I'm not moving at a constant velocity and I'm not pulling the truck. Okay, so that won't work. I could use mu times force normal to get the force friction, but I don't know what mu is, so I can't go with that option either. So the only thing I have left in town is to take mass times acceleration. So what we're going to do on number 1, you found the acceleration. So I'm just going to show you a shortcut way to find mu. Okay? Well, that force friction is mass times acceleration. Well, on a flat surface, how do you find your normal force? It's the same as Fg, and Fg is going to be found by multiplying mass times your gravitational acceleration. So this is basically mg. So what's going to happen to the masses? They cancel out. So you can all you had to do on number 2, if you kind of looked at this in terms of canceling things out, all it is a ratio of accelerations. So to get mu, all you had to do is take the acceleration that you found up in number 1 divided by 9.8 meters per second squared. Boom, there's your value of mu. You're going to get the same answer either way because you multiply both numbers by mass. So that mass, that coefficient of friction on number 2 should be less than 1, but not a whole lot less than 1. Okay? Oh no, it should start in the tens place. Yeah. Something around 0.7-ish. Okay. Now let's talk about number 4. Number 4 is the easiest problem on the assignment. You're going to take 18 newtons, you're going to divide it by 1.5 kilograms, you're going to get an acceleration of 12. It's the easiest problem on the entire assignment. Now, if you look at what's going to happen then on number 5, now we're going to introduce friction. You should have 2 drawings, listen to me, Hunter, 2 drawings done to scale with a ruler. Here's what I want to look for. I want to see every force labeled. I want to see the scale that you used. I want to see everything labeled. The numbers, what the forces are, because if all I see is a random collection of arrows, that means nothing. Okay? Make sure you label everything. Now, when you get the acceleration on number 7, why does your answer to number 7 have to be less than your answer to number 4? Because there's friction. It's working as an opposing force. Okay? So what you're finding on number 6 is the net force. Now, here's the deal. So here's another way that you can understand this concept of net force. Now, not that Maddie would do this, but we're going to use Maddie as an example. Okay? So, Maddie's down to the lunchroom she sees a freshman who happens to have like a nice watch, okay? So Maddie just walks up to the freshman and goes, hey, let's have the watch. Freshman goes, here you go. Okay. Just gives up the watch, okay? So she brings it back to class, it's sitting on there on the table. Kendra sees the watch and goes, wow, it's a nice watch. Maddie goes, I'll sell it to you for 30 bucks. Kendra goes, okay, home run deal. So what's Maddie's net profit? $30, because there's nothing working against her. So that would be like you're launching a spaceship in deep space. There's no gravitational force working against you. There's no friction working against you. All of the force goes to accelerate the ship. Now, realistically, this is what might happen. Maddie sees the freshman down in the lunchroom. Freshman's kind of looking forlorn. Maddie, being the consoling person that she is, she goes, hey, what's wrong? Freshman goes, hey, I don't have my lunch money. Maddie goes, hey, you got a nice watch. I'll give you 10 bucks for it. Freshman goes, okay, that's nice. So Maddie pays 10 bucks. She gets the watch. She brings it back. She sells it to Kendra for $30. What's her net profit? 20 bucks. Because it cost her 10. So even though she's still selling it for 30, she's only made 20 bucks. So that would be like if you're trying to launch something up in the air. You have to overcome the gravity's pull. So when I go to throw this thing up in the air, okay, when I go to throw this, it cost me some money. It cost me some force because I've got to throw it with enough force to overcome the gravitational pull. Now, let's just say, same situation, Maddie is really nice and she gives the freshman $30. She sells it to Kendra for $30 because Maddie really doesn't want to make any money on the deal. She's a nice soul, she just wants to break even. What's Maddie's net profit? 0. So her bank account is going to maintain a constant velocity. Nothing's going to change. Whatever she sold it for is whatever she paid for it. So if you're just applying 30 newtons of force and there's 30 newtons of gravity working against you, or there's 30 newtons of friction working against you, you're just breaking even and you're not going to accelerate. Okay? So as long as your applied force, your FAP, is equal and opposite to your FOP, you're not accelerating. That doesn't mean you're not moving. It just means you're not accelerating. Okay? Got the idea? Beautiful. Now, your answer to 8D, okay? Well, actually, let me back up to number 5. When you draw that tip to tail, which is the second diagram that you have to do, make sure you draw in the resultant, okay? Don't just draw the 4 forces and then leave a gap. How do you draw the resultant? From where to where? Roo.
The kangaroo.
How do you draw a resultant? From where? Origin out. So when you have a resultant, that means that you have a net force. That means you're going to accelerate. So don't leave a gap on your tip-to-tail drawing. That's the whole point, is that you're trying to find the resultant. Okay. Now, when you get down to number 8, because if that goes well, your answer to 8D should be around 200 meters per second. Okay?
What?
Your answer to 8D should be around 200 meters per second. Okay? Everybody cool with that? Now, make sure on 8A, when I tell you, sketch. Now, on 8A, I'm saying just do a sketch. You don't have to draw this from the scale. But here's what I'm looking for. You should have your applied force, your gravitational force, and then a set of vectors for your velocity, and at least one acceleration vector. So those are the things that I'm looking for coming out of 8A. You can do it off to the side, you can do it on another sheet of paper, okay? But make sure, if you want those velocity vectors changing, you draw them so they are changing. If you want them staying the same, you draw them staying the same. And when you're drawing your forces, even though you don't have to draw it to scale, at least if you want one force to be bigger than the other one, draw it a little bit bigger, okay? Don't draw them the same size unless you think those forces are the same size, okay? Now, on the back side, the end of 12.6 seconds, we're going to shut off the engines. So it's like me throwing this golf ball up in the air. As soon as that golf ball leaves my hand, if you look at this equation, that Fnet equals FAP plus FOP. As soon as it leaves my hand, what's my applied force? Don't make this difficult. As soon as it leaves my hand, what's the value of FAP? 0. There is no applied force because it's left my hand. My hand isn't magical and continue to like exert a force on the ball after it's left my hand. As soon as it leaves contact, we're done. There is no more applied force. So what's the only force left in town? Gravity. Gravity then becomes your net force. So if you think about friction, like if I take this remote control and I give it a push, it comes to a stop. So you can think of friction as being like horizontal gravity, which sounds weird, but the only difference is that, and it would be cool, but it doesn't happen. The remote control isn't going to come back to me on a return trip, whereas the golf ball will. So it would be cool if gravity would just stop something and it's like, okay, we're done. And then it just kind of sits there and hovers. Baseball would be a lot more difficult. It's like you hit it up there and then it just gets to that point and just stops. And it's like, what do we do now? Okay. So, when you get to E, there are two distinct sets of drawings that I want to see. And I emphasize distinct sets. You're going to show me, here's what's happening on the way up, here's what's happening on the way down. You're going to have a set of velocity vectors, you're going to have an acceleration vector, and you're going to have a force vector. What's happening on the way up, those three diagrams, and then what's happening on the way down, those three diagrams. So, or sets of vectors, excuse me. So, I want to clearly see, here's what I think is happening on the way up as it's approaching 0. On the way down, it started to fall. What's happening there? Okay? So, do not make me guess, and do not draw random arrows and think, oh, Bergkamp will know what I mean. No, bad. If these are velocity vectors, you label them velocity vectors. If it's an acceleration vector, you label it an acceleration vector. Now, if all goes well on this whole problem, when you get done with your answer to G, your answer to G should be in the mid-30s for time. Okay? Should be in the mid-30s. Make sure on H that you have done everything that I want on that velocity time graph. I want the net forces labeled, I want the accelerations labeled. Yes?
You're including the launch, right?
Huh?
You're including the
Oh,
launch?
yes. Oh, yeah. You got to include the 12.6 seconds. This is not, yeah, no, yeah, boom. That's why I said, from the time it's launched till it reaches maximum height. That this isn't from when we shut off the engines. This is the whole smash. From the time that I light that engine until I see that rocket at its highest point. Okay? All right. Anything else on this? Make sure that you're going to have the vector diagrams from the box. Make sure that you're going to have all those diagrams for the rocket problem. Make sure that everything is labeled so I can clearly know exactly what you want me to see. You know,
This is my command.
whatever.
Hey, that's a good action.
That's you laugh.
You're right, bro.
No, don't laugh. You know it is.
She couldn't say it straight face.
Rick and Morty.
Okay.
I'm always laughing with the pot.
Okay, there you
It
go.
doesn't mean anything.
All right, let's get
All right.
that going.
Hi guys.
So,
Start it.
back to our story.
You weren't in the camera, honey.
Tell me when you can see my ear.
No.
Nope.
Okay,
No. Yeah. There you go. Now you can see.
all right.
It's red. This is the cutoff.
So,
Why?
so what we've got today is something that we'll start today, we'll finish up tomorrow. So, the kind of the ultimate application of every concept that we've talked about so far is launching something into space. So what we've got is it's a series of like 3 different videos we're going to watch, and this is back when we actually had the space program and we were launching the space shuttle. But even though it's talking about the space shuttle itself, it's the same.
Can we please turn it off? It's hurting my ears.
I love space so much. I'm so ready. I love space.
How could you teach?
Okay, all right, better?
Yes.
Okay, I'm gonna turn it back on for a second. So, what we're gonna watch is like 3 different videos. But like I said, even though this is in terms of the space shuttle, we're still using the same technology if you're SpaceX, whatever. There's just a limit to what we can do in terms of rocket engines and fuel and stuff like that. So, I'm gonna stop this a couple times to talk your way through it, but basically, we're gonna sit back and take us about, the whole thing's about 20 minutes to get it.
Start watching a video of a
Are they
video.
gonna watch the video on the video?
Yeah.
A video of a video.
Video of a video.
I think that's a copyright law.
No, it's okay. 'Cause
Try to zoom in.
So,
Zoom in just a little bit. Give them the full effect.
I already found this one.
Alrighty. We're good to go, guys.
Oh yes.
I'm gonna eat my burrito.
Accomplishments in spaceflight have proven to be some of man's most triumphant achievements. The underlying principles which made these achievements possible came as a result of hundreds of years of investigation into the behavior and structure of matter. It's these principles of physics which play the foundational role in making spaceflight a reality. The launching of a rocket provides a spectacular display of force and energy. From a physics viewpoint, a rocket launch vehicle can be thought of as a large force machine. Its sole purpose is to apply a continual thrusting force in order to produce an acceleration. If the rocket is to achieve a low Earth orbit, the magnitude of the acceleration which is required tends to be quite large. The rocket must go from a state of being at rest on the Earth's surface to that of traveling 8,000 meters per second at some given distance above the Earth. This tremendous velocity change takes place over a relatively short period of time and necessitates the large amount of energy and acceleration provided by a rocket launch vehicle. The single most important component of a launch vehicle
now
is
that's
the
actually a
rocket.
Saturn V rocket,
Use
but
of a
that
rocket
gives you
engine
some
provides the
scale
means by which
as far
thrust
as
is
the
produced
size
from
of
a
the
vacuum
engines
of
go.
space. Since oxygen is not present in the space environment, an oxidizer must be carried on board the rocket along with the fuel. The space shuttle's propulsion system is made up of 5 different rocket engines, 3 main engines which use liquid propellant, and 2 rocket boosters which use a solid propellant. The tremendous temperature extremes which the space shuttle's liquid propellant main engines operate at required innovative engineering during their design. The engine's complex system of precision valves and pumps must handle the extremely cold propellants without freezing up. The liquid hydrogen fuel at minus 253 degrees Celsius is the second coldest liquid on Earth. However, when burned with liquid oxygen, the temperature in the engine's combustion chamber reaches 3,300 degrees Celsius.
Okay, so here's where this is a huge engineering challenge. So let's start with the liquid hydrogen. second coldest liquid on Earth. Anybody know what the coldest liquid is?
That's what
Liquid helium, okay? Basically, because this goes into a whole discussion of intermolecular forces, but basically, if you're gonna change something into a gas, like liquid nitrogen, liquid oxygen, whatever it is, you have to get it cold enough so basically when molecules hit together, they stick, okay? So liquid hydrogen is the second coldest, helium is the coldest. So you've got something that's extremely, extremely cold. Now, why do you think we go through the hassle of making liquid hydrogen? Why don't we just use normal hydrogen gas? Like I've got back in the back of the room, I've got a container of hydrogen gas. Why do we go through this hassle and cost of making it liquid? Basically, it's more compact, it's more dense. So, as a liquid, we can get a lot more in the same space. Okay, so that's why we go through the hassle. So you have liquid hydrogen at minus 270 Celsius. Very, 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 very cold. Then you run it through a combustion chamber. Then it basically goes to about 3,300 degrees Celsius. So you've got about a 3,600 degrees Celsius change in basically the exact same system. At 3,300 Celsius, that will melt iron. So within this one engine, you have to be able to take the second coldest liquid we have on Earth, have it go through an expansion process where it heats up, ejects gas at extremely high rates, and at a temperature high enough that it would melt iron. So just dealing with the temperature changes alone was a huge problem. It's like, okay, we got to take something very, very cold, make it really, really hot. So has anybody seen it where you take like glass that's like really, really hot and you dump it in like ice water? What happens? It shatters. Okay, this is why you use Pyrex in the chemistry labs. So that's just a relatively small temperature change. This is a huge temperature change. So just dealing with the materials themselves to make these rocket engines work was a huge challenge. Okay.
Temperature higher than the boiling point of iron. In the combustion chamber of the rocket engine, the propellants are consumed in a combustion reaction. The thermal energy generated from the combustion heats the newly formed gases to extremely high temperatures. These gases, possessing a large quantity of kinetic energy, subsequently go through an expansion in the rocket nozzle and are ejected at extremely high velocities. With the fuel being composed of liquid hydrogen and liquid oxygen, the hot gas which is expelled from the engine is primarily water vapor. The thrust which is produced by the engine can be explained in terms of Newton's third law. As the engine applies a downward force on the gases, causing them to be ejected, the gases must also apply an equal and opposite force, pushing upward.
Now, notice that there's no mention of the platform. Newton's third law applies only within the rocket engine itself. Because if you needed the platform, then as soon as it cleared the platform, then it wouldn't work anymore. Okay? So Newton's third law applies only within the rocket itself. There is no external force applied by the launch pad. We just have to have the launch pad so the rocket doesn't fall down. That's the only reason that the launch pad is there. There's nothing magic about the launch pad. Okay.
On the engine. This upward force pushing on the rocket engine is essentially a reaction force to the gases being pushed downward, and is responsible for giving the engine its upward thrust. Newton's second law of motion, expressed in terms of momentum, can be
We'll
used
talk
to
about
find
that
the
equation
magnitude
later.
of the thrust produced by a single space shuttle main engine. With the propellant gases being ejected at a velocity of 3,600 meters per second, and at a rate of 470 kilograms per second.
Now, to give you some idea, 3,600 meters per second, the speed of sound is about 330 meters per second. So this gas is being ejected at about Mach 10, about 10 times the speed of sound. These particular engines are ejecting gas at about 470 kilograms. that's roughly about 1,200 pounds, okay? That's like a small car. So these aren't the big engines, these are the smaller of the engines. So you're ejecting gas at Mach 10, and it's burning fuel at about a small car per second. That's what each one, that's what these engines are doing. So,
You think that's part of the reason they
it's
canceled?
like, no, okay. So, now, one of the things we're going to look at, if you look at the equation F equals ma, so we're going to do a little bit of rearranging of here. So, the way this is written, it's a constant velocity, which is the velocity of the escaping gas. This isn't the velocity of the ship. This is the velocity of the escaping gas. So basically, it's a function of change in mass per unit of time. So here's what I want you to look at. Imagine that we keep a constant mass and we put this delta sign over here where we have change in velocity over change in time. What's change in velocity over change in time? Acceleration. So this is just basically Newton's second law of F equals ma. So, but instead of keeping the mass constant and having an acceleration, we're keeping the velocity constant and we're changing the mass per unit of time. So all this is just nothing but F equals ma. It's just written a little bit differently.
Canceled the program.
What?
Is this part of the reason they canceled the program? Because it was kind of just a waste of resources.
Oh, no. I mean, no. Part of it was they just didn't want to pony up the money to buy, to invest in a whole new set of ships, which I think in the long run is going to cost us. But that's a whole other political discussion. So,
What do you mean?
all right.
What do you mean it's going to cost us?
In like what way?
The resulting thrust generated by the engine is equal to 1.7 million newtons.
1.7
As seen by the second law, the greater the rate at which the hot gases are exhausted and the greater their velocity, the greater the resulting thrust will also be. Solid propellant engines make up a second group of rocket engines.
These are the big
These
boys.
engines are much simpler in design due to the fact that they require no pumps, valves, or complex propellant feed systems. However, once ignited, they cannot be shut down.
That's the downside.
The shuttle's
Once you
solid
light
rocket
them,
boosters
you
use a
can't shut
propellant
them
which
off.
consists of aluminum powder as
Keep
the
that in
fuel
mind for
and
later.
ammonium perchlorate as the oxidizer. A rubber-based polymer binder is also added. This mixture fills the entire length of the solid rocket motor, except for a hollow channel
Basically, it's a
extending through
Roman
its center,
candle from
which
hell.
serves as a combustion chamber. When ignited, the propellant burns from the center out towards the sides of the casing at a nearly constant rate. An extraordinary amount of thrust is created. Propellant gases are exhausted at a velocity of 3,300 meters per second and at a rate of 4,000 kilograms per second.
Okay, now,
13
Would that
These-
instantly vaporize
okay.
your finger?
Oh, yeah.
If you just like-
Yeah, oh, God. So, these,
Like lightsaber.
these gases, this is only at 3,300 meters per second. So the gas coming out of here is a little bit slower than out of your typical rocket engines with the pumps. But these engines are burning 4,000 kilograms per second. The other smaller engines are burning about 400. So these are basically burning 100 or 10 times the mass per second with about the same velocity. So these engines here are producing about 10 times the force than the smaller engines were. Yes?
So the like polymer on the outside, does it like use that to like ignite it, and that's why you can't stop it? Is 'cause it keeps
Yeah,
burning?
because literally it's like there's no way once you ignite that core,
Yeah.
it's just going to burn all the way through that core. And this is what happened. You guys weren't even born yet. When the first shuttle exploded, I was a freshman, and I still remember this. I was a freshman in college in the chemistry lab at Butler County when the very first one exploded. Because basically what happened, these are held together in sections, okay? And there's a rubber gasket, so these are just stacked together. And there's a rubber gasket in between these that holds them. Well, what happened was that the night before that launch, it got below freezing and one of these seams got compromised. And so as that fuel was burning up, instead of staying within this system, it blew through it, and then that ignited the tank that was beside it, and that's what caused the horrific explosion to take place. But it was bad because there was a gal, one of the astronauts was a gal by the name of Kristen McCoy, who was like, she was a teacher. She was like the first teacher astronaut. And so like all of her kids were watching it. Oh, that's my teacher. And it was on film,
Oh my
live
God.
broadcast. And then, boom. Oh, it was horrible. It was a bad, bad, bad deal. Okay.
Hey, how many
Millions of newtons of thrust.
Huh?
Enough thrust to maintain the flight of 20 747 airliners.
I would guess, hold on. Probably about 20.
20 until
Yeah.
one exploded?
Yeah. That's just me kind of guessing.
Well, that's a decent record, I suppose.
Well, we got it right most of the time.
95% not exploded.
Well, the problem is when it does.
What? Do you hear the ringing? Yeah, I hear the ringing. Do the people hear the ringing? You haven't even listened to that?
The space shuttle system
Okay.
is the most technologically advanced and complex machine on planet Earth. Unlike the Saturn V rocket, which carried its payload to the moon, the shuttle is designed to attain a low Earth orbit. Achieving the necessary orbital velocity is no small task, as it requires the combined thrust of the shuttle's 3 main engines and 2 solid rocket boosters. With the large external tank storing the liquid propellant used by the main engines, and the 2 solid rocket boosters containing their own solid propellant, the total mass of propellant aboard the shuttle equals an enormous 1.7 million kilograms. This propellant mass accounts for 85% of the shuttle's
So
total
this
launch
basically
mass,
is a big
and
flying
provides
fuel
20
tank.
billion
That's
kilojoules
basically
of
what it
chemical
is.
energy, which is necessary for attaining orbit. The filling of the liquid oxygen and liquid hydrogen tanks occurs on the launch pad several hours before launch. The oxygen vent arm, which caps the top of the external tank, allows vaporized oxygen to escape from the tank, and thus prevents the tank pressure from building up to excessive levels. A similar arm allows the lower positioned hydrogen tank to also be vented. As the final countdown begins, the flight crew is taken to the launch site and
Okay, the guy on the right, huge NASCAR fan. Check out those sideburns. Just pointing
and
it
new
out.
orbiter flying with access arm.
Seriously, check out the man chops. Side,
With all
yeah,
systems
NASCAR
checking out
fan.
in working order, the crew access arm is retracted at 7 minutes before launch. At 3 minutes before liftoff, the main engines are swiveled to their proper launch positions. All of the shuttle's engines are mounted on a pivot device, or gimbal, which allows the flow of exhaust gases and the direction of thrust to be controlled during ascent. The oxygen and hydrogen vent arms
Yeah,
retract
you want
at
to
just
get
2
that
minutes
off
before
before
engine
you
ignition.
try and take that thing up in the air.
At 7 seconds before launch, the sound suppression water system starts dumping 300,000 gallons of water onto the pad. This water is used to partially absorb the 170 decibels of acoustical energy given off by the engines, preventing it from fully reflecting off the pad and causing damage to the shuttle. Hydrogen igniters under the main engines are used to ensure that any hydrogen flowing out of the engines prior to ignition is burned off as it emerges. This prevents the buildup of a potentially hazardous cloud of explosive gas. At 6 seconds before liftoff, the 3 main engines are ignited.
Okay, now, we haven't lit the solid rocket boosters yet. Why are they firing just those engines?
Why don't we use this in war? Like, why don't we just...
We do, it's called an intercontinental ballistic
No,
missile.
listen, why don't we just set these on the front lines and just have them do it? And just like whenever they come, just fry them.
So we can do it.
This is like hell.
This really isn't relevant to this discussion.
Literally, it is a subject.
Okay, back to physics instead of warfare, okay? Why do you think they light those 3 engines first?
To have a big applied force.
No, well, they do need that, but we'll get into the force aspect of it later.
So the force on the...
No. Okay, look,
It's kind of like a...
you have 3 different engines firing right there. These work off pumps. So if there's something wrong with them, they can still stop the mission. So like if one of the,
Can't stop
Yeah, the other ones we can't stop. Okay? You don't want the solid rocket boosters firing first, and they're going, and then you realize, oh, you turn on the ignition switch and the battery is dead. Oh, these won't start. Ruh-roh. Somebody go get the jumper cables. No. So you want to make sure that those, there really aren't jumper cables. So, but you want to make sure that those are going before you ignite the solid rocket boosters. Now, even though this is impressive, okay, you've got these 3 engines firing. It hasn't lifted off yet. Why? So right now, if you pulled that launch pad out from underneath it, what would it do? It would fall. Would it fall at 9.8 meters per second squared? No, because you do have some upward force, right? But it's not enough to overcome gravity's pull. Okay? So basically, you're firing these engines, you're making everything is cool. Once we know those are working, then you light the solid rocket boosters.
Shock waves coming out of the throats of the nozzles cause them to vibrate momentarily. At T-minus 3 seconds, the main engines reach 90% thrust. 1/2 second before liftoff, the solid rocket boosters are ignited as explosive hold-down bolts are triggered. During the initial part of its ascent, the shuttle's engines deliver a combined power of over 100 billion joules per second, an amount of power which is equivalent to the output of 85 Hoover dams.
Imagine that.
A distinction can be made between the different types of engine propellant, as the main engines are observed to burn with a clean light blue flame as a result of the hydrogen and oxygen combustion. This contrasts with the solid rocket boosters, which burn with a bright orange flame due to the combustion of the solid aluminum fuel. The dynamics of the launch can be studied in more detail by examining the forces involved during the shuttle's ascent. With the 3 main engines ignited and applying their combined thrusting force of 5 million newtons, the shuttle still remains motionless. At this point, the upward thrusting force represents only a fraction of the total shuttle weight, which is equal to 20 million newtons.
Those birds are getting good.
Was taken away during this period, the net force would cause the shuttle to accelerate downward. In order for the shuttle to accelerate upward, the total thrusting force must be greater than the shuttle's weight.
Watch what
This
happens
takes
off
place
to the
when
right
the
when they
solid
light
rocket
those
boosters
solid
ignite.
rocket boosters.
With the 2 solid rocket boosters applying an additional 26 million newtons of thrust, the total thrust from all engines is now 31 million newtons. At this point, the net force is directed upward and the shuttle lifts off.
Those 3 engines were like.
The initial upward
fraction.
acceleration can be determined by using Newton's second law of motion.
Okay, so this is the heart and soul of what we've been talking about right here. So, this 3.1 times 10 to the 7th meters, that is that your FAP, your FOP, your FINET.
That is, what,
Is 3.1 times 10 to the 7th, FAP, FOP, FINET. FAP, that's your applied force, right? Now, if the space shuttle was launched in 0 gravity, okay, if you were launching from 0 gravity, your FAP would also be your net force, because there wouldn't be any opposing force of gravity working against it. But because we are...
That'd be so crazy.
I know, but just shut up. So, because of the fact that we are on this big rock that has a large gravitational force, that has to be overcome. So, when you look at this force, listen to me. Don't take 3.1 times 10 to the 7th and divide that by the mass to get the acceleration. It's the difference between these two, which is your net force. That's what's get divided by the mass. That's your acceleration. So the only reason this space shuttle gets off the launch pad, or any rocket gets off the launch pad, is if this applied force is greater than the weight of that rocket. Now, an interesting thing happens. As this thing goes up, let's assume that the force from the engine stays constant. As this thing goes up, what happens to the weight of the space shuttle?
It decreases.
Why?
Because you're burning off fuel.
Beautiful. So, as this thing goes up, my weight becomes less. So what happens to my net force? It gets bigger. So as it goes up, there's an interesting thing that happens. Your net force is continuously becoming smaller because it's becoming larger because I'm decreasing my opposing force. So my net force is getting larger because there's less stuff in it. Now, the other side of it, though, is you have to divide by mass. Well, as we're burning fuel, what happens to the mass? Mass becomes smaller. So you're getting a larger and larger net force divided by a smaller and smaller mass, so your acceleration actually is getting bigger. Okay? So as it burns, the rate of acceleration becomes greater and greater and greater. It isn't like a constant value. And we've always talked about acceleration remaining constant. In reality, it isn't. And so, yes?
In deep space, it wouldn't even make a difference. Your mass wouldn't even make a difference. So
Well, it would, because you're still going to be dividing by a smaller mass here as you burn fuel. Does that make sense? Yeah. Okay. All right.
Don't press it yet. Don't do it. Nope.
Total shuttle mass of 2 million kilograms, the initial acceleration is equal to 5.5 meters per second squared.
Dang, that's barely.
No, that's decent. You have to
With the
press
thrust
down on your
initially
car.
remaining
Car's
constant,
gas burner
the
is pretty
shuttle's
good. You get
acceleration
5.5.
will continually increase as the engines expel their propellant and reduce the mass and weight of the shuttle system. With 9,400 kilograms of propellant being exhausted every second, the shuttle's mass becomes reduced very quickly. After only 30 seconds into the flight, the shuttle is traveling with an instantaneous velocity of 200 meters per second. At this point, the engines have already expelled 280,000 kilograms of propellant, reducing the shuttle's total mass and weight by 14%. Newton's second law of motion shows that the acceleration has now increased to 8.2 meters per second squared.
So your acceleration is
At
accelerating.
approximately 50 seconds into the flight, the shuttle enters a critical period during its ascent as its velocity approaches the speed of sound. As the shuttle moves through the atmosphere, it creates a disturbance in the surrounding air. The resulting pressure waves spread out in spherical shells at the speed of sound. As the shuttle approaches the speed of sound, it begins to catch up to the pressure waves it produces. With the distance between wave crests becoming successively smaller, the waves begin to pile up in front of the vehicle, creating a wall of high pressure. This pressure barrier, sometimes referred to as the sound barrier, presents resistance to the shuttle's motion. Breaking through this pressure barrier creates a period of maximum.
Anybody know who the first pilot was that broke the sound barrier?
They die.
No.
no, but using a nice looking.
I know it's a person. I can't
It is a
think of
person.
the name.
10 out of 10 for that answer. Chuck Yeager.
Yeah.
Okay? Chuck Yeager. If you've never, he wrote a phenomenal book, and actually the United States kept the fact that we had broken the sound barrier a national secret for about 6 months before that leaked out, because they thought it was a barrier, like it could not be broken. And that's the reason why, is because as you approach it, they thought it was a wall. They thought that you couldn't punch through it, because everybody else that tried it died. And so it took a specialized ship to be able to pull that off. And so, yeah, Chuck Yeager, first guy to break the sound barrier.
Dynamic pressure and
It was a
results in a
guy.
considerable amount of aerodynamic stress being imposed on the shuttle.
Because the light waves are like.
To minimize this stress, the shuttle throttles down in an effort to reduce its acceleration at the time of passage through the pressure barrier. After breaking through the barrier, the pressure becomes greatly reduced and the shuttle's motion is no longer impeded. With the shuttle no longer experiencing the high level of aerodynamic stress, its engines are throttled back up to 100%. Now, traveling faster than the speed of sound, the shuttle outruns the sound waves it produces. The resulting pattern of waves leads to constructive interference taking place, where successive wave fronts overlap, forming a single very large wave front, which carries a tremendous amount of sound energy along with it. This large wave is called a shock wave and forms a conical shell of sharply increased pressure with the shuttle at its apex. Throughout the remaining atmospheric portion of its ascent, the shock wave will continue to trail behind the shuttle. After 100 seconds into the launch, the engines have expelled an enormous 940,000 kilograms of propellant, reducing the shuttle's total mass to almost half of what it was at the time of launch. With this decrease in mass and resulting increase in net force, the shuttle's acceleration has climbed to 18 meters per second
So
squared.
at this point, you're pulling about 2 Gs. So your arms are gonna feel twice as heavy as they do right
Caused by
now
the
if you go
atmosphere
to
reaches
the
its maximum level, as collisions with air molecules cause portions of the shuttle's exterior to reach temperatures of 1,000 degrees Celsius for a short time. At 2 minutes into the flight and at an altitude of 45 kilometers, the 2 solid rocket boosters have consumed nearly all their fuel and no longer provide thrust to the shuttle. At this point, the shuttle's weight can be considerably reduced by dropping the spent booster casings. The boosters are released by explosive bolts and are then powered outward and away from the shuttle by 4 small separation motors on each end of the solid rocket boosters. The reusable booster casings parachute back to Earth, splashing down in the ocean with an impact velocity of 18 meters per second. With the solid rocket boosters no longer present, the total amount of thrust acting on the shuttle dramatically drops. During the initial part of the vehicle's ascent, a large portion of the 31 million newtons of thrust was primarily used to accelerate the enormous mass of propellant on board the shuttle. With most of that propellant now consumed, and the shuttle's mass only 1/3 of what it was at the time of launch, the thrust provided by the 3 main engines is sufficient to maintain the vehicle's acceleration. At 8 minutes into the flight, the shuttle's velocity has increased to 7,000 meters per second, a velocity more than 20 times greater than the speed of sound. During this time, the acceleration approaches 30 meters per second squared, a value which is 3 times greater than the 9.8 meter per second squared gravitational acceleration experienced at the Earth's surface. To the crew aboard the shuttle, the acceleration of 3 Gs forces them back into their seats as they feel the sensation of increased weight. Although the acceleration causes some discomfort and stress to the body, it is less than half of what was experienced by the Apollo astronauts aboard the Saturn V rocket.
Yeah, they were pulling like 6 or 7 Gs. That was a big concern for them
Cutoff
to
of the
pass
main
out.
engines occurs at 8.5 minutes into the flight, at an altitude of 120 kilometers above the Earth's surface. 12 seconds after main engine cutoff, the near-empty external tank separates from the shuttle. At separation, a small valve in the nose section of the external tank is opened, allowing pressurized gas from the liquid oxygen tank to escape. The escaping gas applies a
Kind of
rotational torque
important
to the
that
tank,
that
causing
they
it to
separate
slowly
that
spin.
cleanly.
This tumbling
Engine
motion
would be
prevents
much more
aerodynamic
difficult.
skipping off the atmosphere and ensures
So basically, that just burns up.
as the tank breaks up upon re-entry, the debris will harmlessly impact within the pre-planned location in the Indian Ocean. With the external tank gone, the remaining orbiter represents only 5% of the shuttle's original launch mass. Having spent all of its main engine fuel, the shuttle's orbital maneuvering engines provide the final thrust for orbital insertion. The maneuvering engines, along with the other engines which are used while in orbit, use a hypergolic propellant. Hypergolic propellants are fuels and oxidizers which ignite spontaneously.
And they're
on
cool,
contact
because
with
literally,
each other
as soon as they
and
come in
require
contact
no
with each
ignition
other,
source.
they explode.
This easy start and restart capability makes them reliable and advantageous for engines which are used a number
So
of
there's no
times while
spark
in
plugs,
orbit.
nothing like that.
At 10.5 minutes into the flight, the 2 orbital maneuvering engines fire to place the vehicle in a low elliptical orbit. The engines provide a total thrust of 53,000 newtons, giving the 95,000 kilogram orbiter an acceleration of 0.56 meters per second squared. The final step in achieving the desired orbit comes at 45 minutes into the flight, as the orbital maneuvering engines fire for a second time, placing the shuttle in a nearly circular orbit at 400 kilometers above the Earth's surface. Having attained an exceptionally large velocity of 7,700 meters per second, the shuttle is able to complete a full orbit around the Earth in only 1.5 hours. surface.
And we'll do all those calculations.
With
In
no
the second
frictional
part of the
forces
class.
present in space, the engines are no longer required to maintain the shuttle's velocity. Its constant motion will continue indefinitely without the expenditure of any additional energy. The shuttle's velocity is entirely maintained by its own inertia, as described by Newton's first law of motion.
Now, so even though it's not accelerating, it's accelerating because of the fact that it's in a state of free fall around the Earth. So once you get it up to speed, then its inertia will keep it going, but gravity will keep it in a state of free fall around the Earth. Now, you have to get up to about, and we'll talk more about this later, why this number is important. But to orbit the Earth, you have to be going about 8 kilometers per second. To give you an idea of how fast that is, that's about 5 miles per second. So that's like going from 53rd and Mays Road down to 45th, 37th, 29th, 21st, and 13th. So you're going from 53rd and Mays Road down to 13th and Mays Road in 1 second. That's fast, okay? So, and the idea being is that matches the curvature of the Earth, because if you're going slower than that, then you're going to fall back into the Earth. If you're going faster than that, you create these very highly elliptical orbits. So that 8 kilometers per second is the magic number to keep it in a state of free fall. Garfield.
Why do the astronauts experience like a bigger force of gravity if the mass of the thing is going down? So why do they experience like a bigger force of gravity?
No, they experience more G's. Okay, they don't, when you talk about G's, what you're talking about is the acceleration due to gravity. Right now, you are under 1 G. Like when you lift your arm, you're lifting your arm under an acceleration of 9.8 meters per second. Okay? If gravity somehow instantaneously became much stronger, and when I dropped something, the acceleration was 19.6, then your arms would feel twice as heavy, because then you would be lifting them under 2 Gs. They're not experiencing more gravity. It's created by the acceleration that they're experiencing being inside the ship.
So,
Yeah, gravity itself is actually a little bit weaker because you're farther from the
yeah,
Earth. Not a lot.
that's what I thought.
No. Don't confuse that with the acceleration caused by the ship. Okay. Now, there's one other quick one to go, and then we're done.
Why make it quick, you know? Alright, so.
No word about it?
No, hey.
So the whole point of this lab that you're going to do is landing on the moon.
Sending a manned spacecraft to another planetary body presents an enormous scientific challenge.
Just the
That challenge
radiation
is
alone is
immeasurably
a huge
escalated
challenge.
by having to also return the manned spacecraft safely to Earth. The extremely successful Apollo missions made a total of 6 different manned landings on the surface of the moon. The lunar module, consisting of a lower descent stage and an upper ascent stage, allowed the astronauts to descend from lunar orbit and set down on the moon's surface. This vehicle was a true spacecraft in that it was capable of operating only in the space environment. Having used its descent engine to land on the moon's surface, the lunar module would be required to do what had never been done before: lift off from a planetary body other than Earth. Due to the extremely different physical characteristics of the lunar environment, the dynamics of launching a spacecraft from the moon's surface greatly contrast the dynamics of an Earth launch. The black sky during the daytime bears witness to the fact that the moon possesses no atmosphere to scatter sunlight.
And that's what Earth would
Because
look
of the
like if we
lack of
didn't
an
have an
atmosphere, aerodynamic stress and frictional drag are non-existent during a launch from the moon's surface. In contrast to Earth launches, streamlining of the spacecraft becomes unnecessary, as the lunar module's protruding components and non-streamlined configuration is of a functional design and presents no problems during launch. In order to provide the thrust required to lift off from the surface and attain lunar orbit, the ascent stage of the lunar module possessed a single rocket engine. Because there was no backup engine and no other means to lift off from the moon's surface, a malfunction could absolutely not be
Yeah,
tolerated.
it isn't like you can
The
call
single
AAA,
engine had to
hey,
work.
my engine won't start. Throw me a
You
bone.
use the most reliable propellants available, hydrazine and nitrogen tetroxide, two compounds which spontaneously ignite upon contact with
Which
each
are
other.
horribly caustic, by the way.
Because the gravitational acceleration of the surface of the moon is only 1.7 meters per second squared, the 5,000 kilogram ascent stage has a weight of only
Okay,
85
so here's the deal. Why is it, if you have that same 5,000 kilograms, that's the number we're going to use in the lab that you're going to do. Why is it easier to launch that thing from the surface of the moon than it is from the surface of the earth?
Because there's limits to gravity.
Yeah, you have the exact same mass, you have the exact same inertia, right? Because it's still 5,000 kilograms. So if you take 5,000 kilograms times 9.8, you get about 49,000. So to launch that thing from the surface of the earth would require about 50,000 newtons of force. To launch it from the moon would only require about 10,000 newtons of force. So it's much easier to launch from the moon because of the fact that you have such a smaller opposing force to overcome when you go to launch it.
a weight 6 times smaller than that which it would have had on the surface of the Earth. Because mass remains constant throughout the universe and is not affected by gravity, the spacecraft's 5,000 kilogram mass requires the same definite amount of net force to achieve a given acceleration.
Now, that's really
Regard-
important. It's going to take the same net force. So no matter where you are, because when you look at net force, that's mass times acceleration. So if I want the same acceleration on the moon as I do on the Earth, my net force is going to be the same, because my net force is mass times acceleration. So remember that, remember that, remember that. Net force doesn't change as long as you want the same acceleration. Whether I'm here, Saturn, the moon, doesn't make any difference. To get the exact same acceleration requires the exact same net force. Now, I might have to apply a lot more force to get it there, but the net force is going to stay the same. Okay, so stop that for a second.
What, that's like, the fire's gonna go out as soon as you. I know, but still, you have to use it.
Okay, are we rolling? Okay, so here's what's going to happen tomorrow. So there's a program on laptops, and I took kind of a program that they had and modified it to fit specifically what I want to do in this lab. So the idea being is that you have the LIM, the Lunar Excursion Module, that you're going to try and land on this launch pad right here. So you can control two things. You can control vertical motion and you can control horizontal motion. This value of the main thruster controls how much force comes out of this engine. And it can range all the way from 10,000 newtons at full throttle to 0 if you just shut off the engine, okay, and anywhere in between. And up at the top of that lab, I've got all the parameters of this thing laid out. The mass is 5,000 kilograms. We're going to assume that that's constant. We're going to use a gravitational acceleration on the moon of negative 1.67 meters per second squared. Okay? The idea being is that you're going to try and get this thing to land right here. As you're flying, I modified this program to keep track of a whole bunch of different things. Your horizontal acceleration, AX, your vertical velocity in the X direction, that's going to tell you which way you're going horizontally. Your acceleration in the vertical, this is this AY column. Your velocity in the vertical direction, and then the value of the main thruster, and then this is just a running clock. Also, you're going to keep like a real-time velocity time graph that's going to keep track of what's happening. This is only your vertical versus time. This isn't a horizontal. This is only the vertical velocity versus time. Anything going right or up is positive. Velocity, displacement, acceleration, force. Anything going left or down is negative. So gravity, your gravitational force is always going to be negative. Your acceleration due to gravity, always going to be a negative value. So tomorrow, you're going to fire up the laptops. You're going to get into this program. And when you open it up, this is what you're going to see. Now, here's the odd thing about this program, and why this works, I don't know. It's always been this way. To clear this velocity time graph, if you click in it and drag it at all, it clears the graph. So that's the only way you can clear the graph in between trials. I don't know why it works, that's just the way it does. So, come in here, hit run, and so then you do a little action going over here, okay. Now, for you to safely land this ship,
You're gonna crash.
I'm gonna crash, it's
Yeah.
okay.
Oh.
All right,
Get off the burn.
so how I set this program up, to safely land this thing, your vertical velocity has to be less than -1. So in other words, like we're saying, if you land it faster than this, the landing gear is gonna break and bad things are gonna happen. So, I was okay this way, I was just going too fast. So, this is what this is showing. So like when I landed, I had a horizontal velocity of -0.28, which means I was drifting to the left. I had an acceleration of 0.17 and a vertical velocity of -1.12. So here's an interesting thing. I obviously landed going down, but was I speeding up or slowing down when I was landing? I had a positive acceleration with negative velocity.
Slow down.
So I was still going down, but I was slowing down as I was going down. Okay, if that makes sense. Now, look at the value of my main thruster. The value of my main thruster is 9,200 newtons. The value of your main thruster is that FAP, FOP, or FNET. Is this my applied force, my net force, or my opposing force? That's my applied force. Okay? That's my applied force. Now, what's working against me? Gravity. Gravity is always going to be working against you. So, here's what you have to be, here's what has to happen for tomorrow. Just like you're not going to walk up to NASA and go, hey, let me take this thing for a spin. I think that's pretty cool. Okay, here you go, Bubba. Here are the keys. No, you at least have to have a rudimentary understanding of the laws of motion. So, what I want done by tomorrow, and here's how this is going to work. You're going to have page 1 and page 1, both sides done tomorrow. So here's what's going to happen. You're going to walk up, I'm going to check through everything. If there is anything wrong at all, it gets corrected before I turn you loose on laptop computers. Because I'm not going to turn you loose if you can't do these calculations. So tomorrow, these get done, I check them over. Once I sign off on them, then I'm going to turn you loose with the actual computer simulation, but not until I check through this. Don't worry about the second page. You can't do that until you actually run the program and you get some data. Okay, so we'll talk about the second page tomorrow. So your only assignment for tonight is to do all the calculations on page 1 and 2. Now, you're going to have to draw some diagrams of forces. You're going to have to draw some velocity vectors, acceleration vectors. So just like you've been doing. Pay attention to the parameters on the top. I've got the mass listed, I've got the acceleration due to gravity on the moon listed, I've got everything listed up here at the top. Okay, we're done, you're on your own.
As long as I don't